people waiting live? I will let people in now, but we'll still wait for a while. Hello, everybody. We are still waiting for some people to join. We will start in a couple of minutes. Please wait.
No problem. Fine.
Well, welcome everybody. We will start. I have people waiting for us on YouTube. So, my name is José Luis Moutinho. I'm from the Air Center. I have Catarina Duarte behind me, behind the scenes, and I'm very happy to welcome you again in the Networking Fridays. Today we have a very, very interesting presentation. I already had the opportunity to go through his slide deck. We have David Ikpaya from the Nigerian National Space Research and Development Agencies, NASRDA. He will present his work for the development of SHACS for global atmospheric carbon dioxide monitoring. SHACS stands for Spatial Heterodyne Atmospheric Carbon Dioxide Spectrometer. I know it's a very long name, and I hope, David will explain the meaning of this long. So this, session is very much related on finding solutions to the continuous concerns of climate change that has been increasing in the recent times. His work could help us to understand a little bit better, to understand, all these carbon and greenhouse cycles, and inform policy makers and decision makers and even economists about how to use this kind of data to go forward in terms of projects related to carbon sequestration. But well, I mean, without any further ado, I'll introduce you to Dr. David Ikpaya. He will introduce himself and then he starts his presentation. The floor is yours, David.
Hello, everybody. Good afternoon. From where I am, good afternoon. And my name is Dr. Ikpaya, David Ikpaya. I'm from NASRDA, National Space Research and Development Agency, NASRDA, Nigeria. And can do a little bit of introduction of myself. And I'm a graduate of physics from the University of Calabar in 2000. Calabar is in Nigeria. I also did my master's and PhD from University of Surrey in the UK. I did my master's in 2000, complete master's 2008, and PhD was in 2014. A pioneer know-how technology transfer a trainee on KHTT program for the build and launch of our satellites, Nigeria Sat-1. That was at Surrey Satellite Technology Limited from 2001 to 2003. And we continued again for the build and launch of Nigeria Sat-2 and Nigeria Sat-X, which I also participated from 2006 to 2009. I have worked in the space industry actually for around 21 years now. And I'm also an visiting assistant professor at the Institute of Space Science and Engineering, an institutional arm of NASRDA, Nigeria. It's affiliated with the African University of Science and Technology in Abuja here, Nigeria. And by the grace of God, I am the winner of the 2022 Research Impact Awards Topical Prize organized by the Commonwealth Scholarship Commission, having participated as and won the award for the Rutherford Fellow, 2017 Rutherford Fellow, which I continue the work, which you will see in a few minutes. Yeah, so that's me. Happily married with 2 children. Thank you. So,
can you share your presentation? Yeah.
Yes, please. Okay.
Can you share? Yeah, go.
Can you see my slides, please?
Yes. Okay, perfect.
Okay. So, yeah, good afternoon again, everyone, and welcome to this Networking Friday session. I'll be presenting on development of SHACS for global atmospheric CO2 monitoring. And I've already introduced myself. I'm Ikpaya, David Ikpaya from NASRDA, Nigeria. NASRDA stands for National Space Research and Development Agency. In today's presentation, I'll go through, give you an introduction. And then in the course of the introduction, we are going to identify the gaps which needs to be filled, and then provide solution to the gaps which you'll see, and then we go through the scientific requirements required to do the, to fill up, to give provide a solution. Then we do a bit of intro to the atmospheric modeling, CO2 modeling. Then the next one will be to discuss the instrument technique which we use. and then also goes through the build and test process, and then to the measurement campaign. Then we analyze the results, and in the course of that, we will discuss the UN Sustainable Development Goals that we've achieved, and then we conclude. As we all know, climate change has been of concern to everyone in recent times. And of course, efforts are targeted at mitigating its effects. And these efforts include using satellite observations and in-situ terrestrial networks because they play a key role to understanding and managing the problem. However, due to the sparseness of the in-situ networks across the tropics, especially along the equatorial region, it has made the identification of CO2 sources and sinks to be subject to significant uncertainties. And this is where we then come in. And as you see in the next slide, that CO2 just keeps on rising. This result, which you see here, is from a recent one from the Manalo Observatory. And as of December last year, CO2, atmospheric CO2 had gone up to like almost 418.95 parts per million. And it keeps going, it's still on the increase since the industrial era, rising all the way from 280 parts per million to what we have over 400 parts per million as at today. And the global carbon cycle, which is necessary for us to show this, tends to bring us why we need to solve this, help us to understand what we are facing, and so that we can also be able to solve the problem. Nature has a good way of balancing itself. The atmosphere, the terrestrial biosphere, and the oceans. There tend to be a fairly good mix of the carbon, and so we call it the global carbon cycle. However, due to human activities, fossil fuel emissions, the land use change, and other human and anthropogenic activities going on, that disrupts the balance in the atmosphere. We keep pumping in more carbon into more CO2 into the atmosphere. And that is the reason this keeps increasing. And as that continues to increase, the effect of the global warming is stretched, and we feel it more. And the adverse effect is what we experience as the climate change. And when the studies have been able to calculate and this to see what is how this can be resolved, and they found what they call the budget imbalance. And so the budget imbalance, although that figure has drastically reduced in recent years, this imbalance is still there, kind of giving us the uncertainties that we are talking about. And we know that the terrestrial biosphere holds the central role to this carbon cycle. And it also has the key to this imbalance, and is a reason that we are looking into it critically, terrestrial biosphere, to resolve it. How can we better do this is where we profile this solution, that there is need for finer spatial and temporal resolution of measurement of atmospheric CO2 concentration. So this requires both space-based and space-based monitoring to fill in the gaps in the terrestrial measurement networks. And these terrestrial measurement networks, although they are there, but it's very sparse across the tropics. And the solution is to have a constellation of CO2 monitoring microsatellites. For us to build this CO2 monitoring, these microsatellites, there are ones existing out there, which we know that they are characterized by their very large size and they are very expensive. And some are very complex because of the technique of design, what is involved in building it. And so we then look into it critically on what we can contribute, be putting as a contribution to solve this climate change problem. And that means we have to meet key scientific requirements in building, profiling this solution. So one of the key requirements is to observe the CO2, as we know in the week, the CO2 in the 1.6 micron region and the 2.0 micron region. That's where the strong CO2 exists. Of course, it will be incorporated with the oxygen A-band module. And of course, the instrument itself must meet a spectral resolution of 0.27 per centimeter at full width half maximum, achieve a high signal to noise ratio at the various frequencies which we are going to operate from, and a measurement precision of less than 1%. This is very stringent criteria to meet. And of course, we aim for a high spatial resolution for clear sky soundings. These clear sky soundings must be devoid of clouds and aerosols. And so the principles of observation is what we're presenting here. And so here we have the sun moving down into the atmosphere. They have interactions in the atmosphere. I hope this animation is well seen across the viewers. So, and then this since the CO2 has its own spectral signature, which is what the satellite looks at and picks up this spectral signature, and that's done through the measurement of the absorption of sunlight that is either reflected from the Earth's surface or is transmitted through the atmosphere. And as I said in the previous slide, we are looking into the CO2 absorption spectrum at 1.6 micron region and the 2 micron region. The reason for that is that they provide very high information on near surface concentrations of CO2. And the CO2 is mostly variable in the lower troposphere. And so then we then did a model to understand how the CO2, which part of the spectrum that exists. So we did transmission model of the CO2, and we found out that in the 1.6 micron region where we have the weak CO2, it was potentially free of water vapor, and the 2 micron region of the spectrum is very high. It has a well mixed with water vapor. However, these two channels are required, or these two spectrums are required to be able to characterize a CO2. Of course, it must be incorporated with the oxygen A-band channel to correct the AMRs and the cloud effects. And we then pick that out. For us to do this, we'll be focusing for the rest of the presentation on the 1.6 micron channel to do a prototype, build a prototype, test it to be sure that we can actually meet these conditions and be able to contribute to solving the issues at hand. Now, there are various techniques which we can use, but let's just look at 2 broadband spectrometers, 2 types. We have the dispersive one and the interferometer one, the Fourier transform spectroscopy. For the dispersive spectrograph, the light must pass through a slit and then gets dispersed by fixed grating onto a two-dimensional detector, like a CCD. Then for a Fourier transform one, or for like a classical Michelson interferometer, light gets through the aperture and gets split by a beam splitter through the moving mirror. Then that creates a recombination of the wavefront, which is recorded on the photodiode. A Fourier transform of that yields the spectrum. But the concept which we're going to introduce is that of which had been done by called the Spatial Heterodyne spectroscopy, which was developed by Hollander and Rosler in 1991. It takes advantage of the Fourier transform spectroscopy and eliminates the moving mirrors. It removes the moving mirrors and replaces with its diffraction gratings. And you'll see that with that, the wavefront is then reconstructed and captured by a two-dimensional detector. You do a Fourier transform of that, and then we get the needed spectrum. This technology or this technique has been applied in the extreme ultraviolet, the vacuum ultraviolet, the UV, the visible, infrared, and long wave infrared spectrum, and mostly focus on the emission spectra. So for us, we're going to take advantage of the SHS, the Spatial Heterodyne Spectroscopy, who has very high throughput through the entrance aperture, which we saw in the previous slide. And it's compact; it does not have any moving parts, and develop what we call the Spatial Heterodyne Atmospheric CO2 spectrometer, called SHACS for short. So it uses the SHS technique, and we use reflection gratings there, and then have the beam splitter, same configuration of that of the SHS, but now we apply it in a broadband spectrum. This is very unique because we've incorporated a short-wave infrared filter and uses the in-gas detector to record the interferograms, get the spectrum, and then we start analyzing what we've got. So this method, we had to model it, or then model the SHACS in optical model so that we can understand how it's going to look like. And the model here, we have the first channel called channel 1. And initially, let me point out here that this instrument was known as the COMSWARE instrument, the Compact Spatial Heterodyne Shortwave Infrared Spectrometer, which was later renamed as SHACS for short to make it simpler. And so it can be used for both terrestrial-based monitoring and space-based monitoring. For terrestrial-based monitoring, there's an optional scanning mirror which we have introduced. And you'll see a reason why we had to introduce the optional scanning mirror, so that the instrument will not be moved around. It's a bit tasking during measurements. Or we can mount the instrument on an auto-sun tracker if you don't have the scanning mirror. And so for this, and of course the size of this is same as that of a typical microsatellite platform, which is about 60 cm by 60 cm, such as the Nigeria Sat-1 or Nigeria Sat-X microsatellite, or the class of the UK SSTL, sorry, satellite technology 100 gram 100 kg class of satellites. And so this is the space-based model of SHACS, which has the channel 1, the first channel, And then that's a 1.6 micron channel, and the channel 2, second channel, that's a 2 micron channel. And of course, the 3 mirror astigmatic telescope, we call it TMA. And of course, the size is still that fits into a microsatellite platform. And then we did a proof of concept of that, made a demo to demonstrate what we have. The essence of this is targeted of retrieving quality interferogram. That's the essence, so that we can process it and retrieve back our CO2 spectrum. So here we have a light source as the halogen lamp, and then set up the instrument in the lab, everything that we've shown you earlier. And this is the way it operates. I hope this you can see this animation showing you the light gets collimated and then gets split up at the beam splitter, recombines the exit optics, and then passes through the filter, special filter, and gets recorded on the detector. And then the first thing we do is to get the retrieve, trying to understand, setting that up, which you've just seen, was to set the instrument in its literal configuration. That means we are going to have a zero path difference, get a zero path different fringe line where there is a constructive interference at the detector. And then we tilt, do a cross tilt of the detector of one of the gratings and get our interferogram. Then you can see from here that the detector had some defective pixels, which we put it in 3D form to eliminate or to take out the defective pixels before doing our trying to retrieve our spectrum. And in the method for that requires us to have to get a filter profile first. The filter profile is as a result of the input spectrum, and which yields the output through the special filter. And so they now have this broadband spectrum. So we have the filter profile. We then superimpose the filter profile on the simulated CO2, which we did earlier. And then we carry out a Fourier transform of that and focus only on the modulated part of the interferogram. The modulated part of the interferogram is then inverse Fourier transform for us to retrieve our spectrum. So that is the technique, and that is what we did to get this qualitative part of our work. And then, having concluded that, I must say at this point, my PhD was, which was sponsored by National Space Research and Development Agency, NASA Nigeria, through one of its activity centers, Center for Satellite Technology Development, CSTD, NASRDA, Nigeria. I was then completed. And then the next phase of this work, which we continued, was sponsored by the Commonwealth Scholarship Commission, the UK. And so in this phase, we needed to take out the instrument from the lab, the previous lab where it was, because we could not channel in or reflect sunlight or have access to sunlight into that particular lab at Surrey Space Center, University of Surrey. So we moved it into where we could reflect sunlight into the lab. You can see here, I have channeling through a flat mirror, reflecting sunlight in here, and then you can see the sunlight passing through the door into the instrument. And the setup is so robust that even after movement, moving the equipment around, we're still instrument around, we're still able to get our interferogram and record our interferogram. Then, having achieved that feat, all this is in preparation for open a measurement of the total column CO2. So it was then we then had to mount the instrument on a
hello, David. I guess we stopped listening to your presentation. Listen, Katarina, are you listening to?
No.
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 Yeah, sorry. Oh, okay. Okay. You'll be back soon, I'm sure. Hello, David. We missed some. Yes, hello. I guess you had a networking problem. Yeah.
Yeah. Oh, okay.
You can reshare your presentation, please do.
Okay. Sorry about that. Can you see my presentation, please?
Yes, we can. Yes. Yes. Can you put in? Okay, good, perfect. You can go on.
Okay. All right. So I repeat the previous slide. I'm not sure at which point. I think this was okay. So here was when we set it up in the lab to reflect light into the lab, and then we now had to take it out into the open air, set it up on this microsatellite platform base. And of course, as this microsatellite platform base was such that it can counter, the instrument setup was such that it can counter any form of stray light, because we are now operating in the open atmosphere. And this was
sorry,
done,
David, we can't see. Okay. We couldn't see your screen. Maybe you should turn off your camera. Maybe it's
okay.
It should be, okay.
Okay. All right. Sorry about that. Can you see the screen now, please?
Yes, yes.
Okay. All right. So, so this instrument was mounted at developed this stage of work was developed still at Service Space Center, UK, and where we then started to do our measurement, our campaign, and the results, even taking it outside and mounted here, yielded this quality interferogram, which we have seen. And so we then commenced the total column CO2 measurement, which means daily monitoring of atmospheric CO2. Measurements were taken from as early as of the morning, as soon as the sun is up. That was in 2019, May, June, throughout the summer period. And so as sun gets up, once it's up to 7 degrees above the horizon, we start measurements. And then we also have to pause the measurements because we're manually moving this instrument, which is why I'm saying that for terrestrial-based monitoring, it's advisable and to be good to mount it on an ultrasound tracker or having a scan mirror mounted to channeling follow the sun all the way through, because the Earth is rotating at the speed of 463 meters per second. And so that means we have to move this and take data every 2 to 3 minutes. And having done this sometimes I will require the help of maybe like you can see the guy here, the PhD student at that time. He has completed his program now, Callum, and then we can move it together, try to move the instrument. But then we take the measurement. I take the measurements every 2 to 3 minutes. I have to do this sounding fast. When the sun is at 12 o'clock position, we pause, because if we continue, the instrument may tumble over. And then we continue again when the sun is about at 2 o'clock position, all the way to sunset. And the results were phenomenal. I mean, it was amazing. Very, very high quality interferograms were recorded in this compact instrument. And then we do put the same way we are discussing the retrieval process. This is a sunlight retrieval, which we superimpose this spectrum on the simulated spectrum, and everything fitted, the absorption lines fitted each other, just for the want of time, and we didn't put that in here. For each measurement, each clear sky measurements must be devoid of clouds, which you've seen here. This sample was just a clear open sky Asura, which I took in one of the days doing the measurements, for you to know that this is done at clear skies. And we must have handheld instruments. We have handheld CO2 measuring instrument, temperature and pressure. So this provides us with the a priori information. This is necessary for the iterative retrieval process to retrieve, to know the actual CO2 concentration which we've recorded. Another important, criteria to meet, which, if you can recall, the scientific requirement was to meet signal to noise ratio. And so this is a function of the source brightness, entrance, aperture, optical throughput, integration time, and of course, the detector performance. And the signal to noise ratio is the end performance metric that determines the ability to collect spectra. So we did a simulation of signal to noise ratio of our instrument, signal and the shortwave infrared, and we got about above 700:1, and that was very good. And then in actual measurements using the halogen lamp, which the one in the lab, we tested, was 564 as a seal greater than 300. Then in sunlight, at our center frequency of 1.6 micron, we got 990. So that was very, very high, and this shows that this instrument has very, very high performance. And then the next stage, having completed that, was now to do the iterative retrieval process to be able to know the CO2, beautiful CO2 spectrum that we've retrieved, we've gotten, what is the CO2 concentration, so that we can actually determine the subtle changes of CO2. And that process required us to do what use this method by called the inverse model. And then the inverse model was introduced by Rogers. And we've also consulted other literature, like the work of Hartmut. And then so we then carry out the retrieval process, the iterative retrieval process. It's required knowing what the formal, the forward model is, the forward model, the state vector, of course, the a priori value, the covariance metrics, and all the Jacobian metrics, that's the weighting function. You put in all that to be able to retrieve the measured CO2. And the spectral resolution was very high of what we got, better than what was stated, was 0.22 per centimeter. Now, let me state that in each sounding, we have about 30 frames of interferogram, which was sampled at about 0.3, interval of 0.36 seconds. So the detector was actually very, very fast, capturing those frames by about 30 samples per second. And the total that we see for each, for like a collection of sounding, is about 600 samples per data collection sequence. That have to be iterated for us to know the average CO2 concentration for that. So it's a lot of data that's built up over time, over time that we have been analyzing. So for each, you get the average CO2 concentration, you record it, and then you move to the next sounding and record the CO2 concentration. And the average CO2 retrieve had to be done through an automated process. We use data assimilation approach. And you can see the trend. This slide shows the CO2 trend for that of May 15, 2019. And the next one is that of June, 6th of June, 2019, both out of morning and the evening. So you can see how it varies, how CO2 varies. And then we then do the atmospheric profile, CO2 profile. The profile was based on the CO2, which we know is variable, varies greatly on the Earth's surface, around the Earth's surface. That's the lower troposphere. And so we can only do the profile up to 2 kilometers. And this is the profile for a few measurements which we did on the 6th of June 2019. And the cyan lines here is the measurement precision of our instrument. And we're able to record, have achieved an average measurement precision of 1.27 parts per million. And I'm pleased to say that this is about 0.317%, far less than the requirement of 1%. So these instruments can actually be can be used to solve this, to better understand CO2 emissions. And for a typical coverage analysis focused on a space-based model, mounted at an altitude of, for a satellite operating at an altitude of 700 kilometers, we have a spatial resolution of 118 meters. And since we are doing a regional sounding, and of course that covers a total swath of 15 by 15 kilometers without scanning. But since it's regional sampling, a constellation of about 5 satellites of there will have about 9 hourly global coverage of every region. And with that, we can be able to know where CO2 is. And of course, that can be augmented by the, complemented by the terrestrial measurement hubs. And then we now look into the UN Sustainable Goals that we've addressed by this instrument. Of course, topping the list there is the number 13, climate action, without that needed to be explained. And then followed by number 3.
Oh, it seems that we lost David again. We'll wait for a minute, please. Please stay tuned. We'll be back soon, I'm sure about that.
We've been able to monitor atmospheric.
Excuse me, David. Excuse me, David. I mean, we couldn't hear you after you started with SDG 3. Can you start again?
Oh, okay. Okay. Yes. Sorry. We've been able to address about 13 UN Sustainable Development Goals, and I've said topping the list there is the climate action number 13, and then followed closely, that does not need much of explanation, then followed closely is number 3, good health and well-being. If you have good monitor CO2, we'll have good air quality, and that greatly improves health. And then we then move to number 7, affordable and clean energy. Of course, we are looking at reducing CO2 emissions and monitoring that to ensure that only clean energy will be mostly used by all. And so this research addresses that as well. And if we then look at number 10, we can see the essence why we focus on looking at doing this measurement along the tropics. Because if you look, the equatorial region holds most of the abundance of the terrestrial biosphere, the Amazon forest, the sub-Saharan Africa, and then, but the networks are very sparse along this region. And so this inequality can be reduced if these measurement networks are spread across these regions. And so that addresses number 10. And if you look at number 17, if we look at partnership for the goals, if we partner with each nation, if we partner with nations across the tropics, we've actually addressed number 17, because for us to mount our SHACS instruments there, we need to have discussions, we have understanding with the government, and then that is improving bilateral relations among countries. And then we then move over. By doing that, we've effectively addressed 3, no poverty, because it's going to create employment. We've addressed 0 hunger. There will be food for everyone. And then we've involved, they'll do number 5, gender equality, because everybody will be involved in this work. The measurement hubs to be manned by people or manned by stations, and then this information is going to go out. And then that, of course, creates a decent work economic growth for the community and for those areas, and addresses number 8. And of course, this research is focused on, is an innovative research. And so that addresses number 9. Sorry about that. Address number 9. And finally, number 11 and 12, sustainable cities and communities, which we're talking about green energy. Since you want to have cities that are sustainable and not to be focused on the greenhouse, the CO2 emissions. And then, of course, this effectively is tied to number 12 as well, which is responsible consumption and production. So if anybody is doing something there in terms of energy research, so it has to be clean. So you can see that we've addressed 13 UN Sustainable Development Goals effectively, with including number 15, life on land. If we have a good atmosphere, we have reduced CO2 emissions, we can monitor compliance, and life will be better. Life will be better for everyone. And so in conclusion, we have we've been able to achieve high precision measurements of 0.317%, I've said, far less than the requirement of 1%. This instrument is suitable for both space-based and terrestrial-based atmospheric CO2 monitoring. It's very cost-effective, and we can have measurement hubs across the tropics. And also we can focus especially on we also have the space-based solution. We can focus on the sub-Saharan Africa. It promotes bilateral relationships, which are already explained in the SDGs, and through the setting of measurement hubs. It also provides a platform for technological advancement across sub-Saharan African countries, and of course across the globe. And we support policymakers to ensure compliance from all countries to reduce carbon emissions in response to the global climate crisis, where it has been able to address 13 UN Sustainable Development Goals, as we've seen. And for future work, we intend to build and test the second channel and the O2 A-band channel to complete our instrument. And of course, also develop ultrasound tracker for terrestrial monitoring. Please permit me to appreciate NASRDA, the National Space Research and Development Agency, for giving me the opportunity to undergo this research, of course, through the Center for Satellite Technology Development, CSTD, NASRDA, and University of Surrey, especially Surrey Space Center, for always having me finishing my PhD, going back again to do my postdoc, to take this instrument to the next level. And of course, the Commonwealth Scholarship Commission that were through the Commonwealth Rutherford Fellowship Program. And these are my references. And I say thank you very much. Any questions?
Oh, thank you so much. I mean, thank you so much, Dave, for a very thorough presentation. I learned a lot, and I hope other people learned as well. Can you turn on your camera?
Okay.
So yes, perfect, good. So we have, I go through 3 questions that we have here on the question and answer. And I mean, the first question is from Eurico Gutierrez. I assume he's from Colombia. And actually, he has 3 questions. Dear Ikpaya, thanks for your presentation. I understood that you need clear skies to measure CO2. Colombia is covered by clouds very often. How do you solve this problem? The second question is, can you link your measurements to specific regions or countries? How do the atmospheric circulation influences the measurements? I mean, greenhouse gases could be produced in one country, but would impact other countries. So let's start with these 3 questions.
Okay, I'll address the first one and the second one together. Yes, okay. We need clear sky soundings, and that is why one of the requirements for us to meet was having a high spatial resolution. And we've achieved that by having 118 meters as for our resolution, spatial resolution. And with the instruments, there's a gap between the clouds. For measurement to be taken, such example what we did at Surrey, when we have the clouds coming over, measurements are stopped. We pause measurements. Or if measurements are taken, those measurements are discarded. This is why, even though we have about 600 samples, during the iterative process, it looks true. Each of the spectrum with clouds is eliminated, and so is not taken into account. And similarly, so that can be applied for Colombia. Colombia is not different from the Niger Delta region of Nigeria. It's mostly cloudy all year, and only around the December period that we have about a week or 2 of clear skies. So it's the same technique can be applied. And so that's we've achieved this by the high spatial resolution, which takes care of that problem. And then the last question is how to linking the measurements to other networks. Yes, that's why we need to have our setup, the measurement hubs within the region. And yes, CO2 is very, very variable and very dynamic. And that occurs mostly at the lower troposphere, which you saw there in that profile. So when we complement the data or the result, the measurements retrieved from the measurement hubs that we have, the terrestrial measurement hubs, then we combine that with the space instrument. Then we'll be able to resolve which region is actually was responsible for the CO2.
Oh,
so with the space-based and the terrestrial-based measurements, so that is taken care of.
Oh, that's how you link in-situ observation with satellite-based observations. Yes. Makes a lot of sense. So the second question is, congratulations for the very detailed presentation. I would like to know if all these technologies proprietary, or you have plans to open the technology for further appropriation in emerging economies, such as Southern Africa.
Yes, it's proprietary at the moment, but as we progress to complete the full instrument, then it will be open. But I've done publications out there, such as the one that has won the award, which if you go through that, it's very easy to even understand what we've done. And so yes, it will be open in due time for companies and others to key in and to join us to make the world a better place.
Oh, that's a good. As you may know, I mean, appropriating these, open technology is very important for the development of competence and skills, in emerging economies. So this is good news. So we have another question from Zachary Suhu. Which collaboration do you have with the Research Institute in Nigeria? Students can collect data for free of charge?
Oh, okay. Thank you very much for that question. Currently, the instrument itself is still at Surrey Space Center in the UK. So it's not yet here in Nigeria. That's why the only information we have is that of the data that we had is with that of 2019 to 2020. So that's the series of data that we have. So the effort is in progress. So we have the plans of bringing the instrument down to Nigeria to set it up and also do measurement, like daily measurement, because currently it's just lying fallow there at Surrey. So as soon as we do that, data will be free, and of course, especially for students to continue their research.
That's good news. This basically answers as well Zachary's second question. If that will be available for everybody or for by request. If it will be open, people can just download, or they will have to request this data to be downloaded in the future.
Thank you.
Yeah. So now, we still have some more questions here. So this is Dr. Suleiman Sadiku from Futmina, from Nigeria. He's he always with us at the Networking Fridays. And he says, well done. CO2 is necessary for life, photosynthesis. How do you reconcile this with your position on CO2 emissions? So how do you know this is, normal, natural CO2 emissions, and which part is, man-made emissions? I guess this is his question. Yeah.
Yes. I can tell you from experience what we did at Surrey. If you look at I don't know what the presentation, the final slide is still open. You can see where the instrument is lying there. During part of our measurements, we have induce activities through vehicular movements, because sometimes it's close to the road where we are taking these measurements. And we have, because it was summer period, and so we have the lawnmower going around to mow the lawn. We also have student activities coming out to have a picnic, or to get around during the summer period. Now, all these activities introduce a spike in the spectrum. And so it's easily identified through the measurement. So the actual measurement we're going to see, you'll see that it's going to be away from the normal. And so away from the normal, because you require to have your a priori information, for example, the handheld calibrated tools, to be able to know what is expected, what is kind of expected, and then you're able to use that to then validate what your measurement is. And so you're able to know, especially when the lawn mower is around doing cutting the grass, you'll see that the very, very high spikes in the atmospheric CO2. Now, what the measurement that we receive. So we're able to eliminate that is not the case, that is not the real case for the day. And so we wait again until when everything is settled, and then we continue measurement. So though this is how we're going to do the same for whatever region, to know what is the normal situation and irregular activities. And so because it's the spectrum we are looking at, if there are plumes from industries or from plumes of CO2 or pollution into the atmosphere, it can be picked up. And I must say here that it's not only methane and CO2 that this instrument can pick. We can tune the instrument to also look at methane, interestingly, by just tuning the grating. So we pick up other greenhouse gases, not just CO2.
Okay, good. Thank you for a response. We are on time, but I still have 3 questions for you. I hope the audience understand. Then, how do you intend to cover the tropics with your SHACS instruments?
Okay, that will require funding. It will require bilateral relationships among nations, across nations in the tropics. And so if we get into partnership with the countries and have funding, then it's just to develop, establish measurement hubs, CO2 measurement hubs in these regions. And so that's how, that is the plan, and that is the way we know it's gonna go. But it's boiled down to having access to funding.
Yeah.
And though also for the space-based method,
yeah,
we need to have a constellation of satellites, or CO2 monitoring satellites. And so this makes it, this facilitates and improves what we call the high temporal resolution that we are looking forward to.
Oh, thank you. So it goes, you just mentioned funds, and go to my final question is, I mean, all these carbon schemes for fund schemes for monitoring CO2, for carbon sequestration, how can this help your research and to go forward and develop the full, sensor as you showed in your presentation?
Yeah, as I showed in the presentation, and for us to complete this instrument, we'll still require to build a second channel, of course, a telescopic module. However, if we, just like you've talked about the access to funding, if we have access to the funding from that body, and then we just have to put in applications and put in our requests in there, and see if we have access, then we can develop this instrument further.
Yeah, I hope you can help to link up your research with some providers of funds related to greenhouse emissions very soon. So, we'll close the session in a few minutes. We have no more questions. And do you want to say, do you have some final words for the audience?
I just want to appreciate everyone who created time, had time to tune in and to listen to this presentation. Thank you very much. It's very much appreciated. And also to thank, again, to thank NASRDA, thank Surrey Space Center, thank Commonwealth Scholarship Commission in the UK for this opportunity given to get this research to this level. Yeah. So thank you, everybody. I'm really grateful, and we look forward to having you know, this instrument going around doing its work, taking measurements and solving the climate issues globally, and at a cost-effective, a very cost-effective solution. Thank you so much. Thank you.
No, thank you, David. We'll put you in contact with some of the people that in this audience, so we could, well, further develop these relationships created in this meeting. Thank you so much. And I see you soon next Friday, you all. Thank you, David.
Thank you.
Bye.
Thank you. Bye. Bye.